Good day, everyone. Welcome to our module or discussion for today, which is about number theory, specifically on the divisibility of numbers. This is part one of number theory. Part one will be about divisibility, and part two will be about um, the number systems. Okay. Now, let's start with these definitions. We have when you divide a number, so that's read as b divided by a, or we use the symbols. The division symbols is one now for division, and also this one denotes division. We can also read this as A divides B, and thus express as in this form. Okay, this is read as A divides B. We can only say that A divides B if b divided by a is an integer, meaning the quotient or the result is an integer. Here, a is called the divisor and b is called the multiple, okay, or the dividend. Okay, if a divide b is false, then we'll put a slash, no, on the bar. Okay, this is how we write a does not divide b. This means that when we divide b by a. Now, when we divide b by a, there is a remainder. Okay, that could be one or any number. So we can only say that a divides b if when we divide a from b, the remainder is 0. Okay, let's have this example. True or false? Does a divide 9? Yes, of course. This is true. Does 3 divides negative 9? Yes, because 9 divided by 3 is negative 3. Does 4 divides 5? Of course not. Okay, so we will put a slash here. Okay, that's 4 does not divide 5. Does 2 divide 9? No, also. Does 8 divide 0? No. I think it's yes, no, because 0 divided by 8 is 0. There is no remainder. 7 divides 7 is true, and that's all. Okay, we'll have a special topic for this 8 divides 0 later. An explanation will be discussed later. Now, first operation in the number theory is about division algorithm. So we know how to divide already, but what's the algorithm when dividing a number? We'll also be discussing greatest common divisor, prime numbers, relatively prime numbers, least common multiple, and the phi function or the Euler-Stoichian function. Let's start with division algorithm. Here's a theorem. If a and b are elements or are integers, this is the set of all integers. So if a and b are integers with b greater than 0, then there exists a unique q, which is quotient, and a remainder, which is also an integer, with a is equal to q times b plus r. And again, r is greater than or equal to 0 or less than b. So where a is called the dividend, b is the multiple or the divisor, and q is the quotient, and r is the remainder. For example, determine the quotient on and remainder of 23 divided by 8. Now, if we will use this theorem, how would we solve it? Okay, let's write here in top. So for number 1, So write 23 divided by 8. So how would we write it using division algorithm? Now remember the equation. You have A is equal to, the dividend is equal to the quotient times the divisor plus the remainder. So where is A? Where is B? So A here is this one. This is the divisor, and this is our, no, it's, this is A, sorry for that, and this is B. So we'll have 23 is equal to Q times B, which is 8, plus R. How would we solve this? How would we find the quotient and the remainder? We will start with the quotient. No. What do we multiply to 8 so that it would result to a number equal or less than 23? Now let's try multiples of 8. Okay, the multiples of 8 are 8 times 1, which is equal to 8. You also have 8 times 2, which is equal to 16, and 8 times 3, which is equal to 24. However, here, as you can see, 24 is greater than 23, so which means our Q is located in this portion, and that is number 2. So we'll now have a Q, which is 2 and multiplied by 8. How do we get the remainder? So we now have 16. That's 8 times 2 is 16. So we will subtract 16 from 23. So what is 23 minus 16? The result is 7. So our R is 7. Therefore, our Q is equal to 8 and R, which is equal to 7. So this is how we get the quotient and the remainder. How about this? So I want you to solve for this one. I want you to show your solution for this question. What is 100 divided by 7? What are the values of our quotient and remainder? So I will just tell you the answer. So you have to provide the solution. Um, I think you can immediately show the solution. I'll just show you the answer. So this is Q is 14, while the remainder is equal to 2. And you have to take note of this condition. R should be greater than or equal to 0, and it should be less than B. So here our B is 8, so it's our R, no, is greater than or equal, is greater than 0. Diba? 7 is greater than 0, and 7 is also less than 8. Okay, so here, so I'll just show the solution. So we'll have 100 is equal to 14 times 7 plus R, which is equal to 2. Our quotient is 14, our R is 2. Okay, if we check this condition, 2 is greater than 0, and 2 is less than our B, which is 7. Okay, so that's how we use division algorithm. Next, we still have a, okay, another definition for division algorithm. We can also rewrite this as Q is equal to A divided by B, no, or A divides B. Okay, And there is a remainder, which is A modulus B. So what is modulo? Now modulo, again, this is the process when getting the remainder. So in the previous slide, okay, it's not here, so I'll just explain it this one. Say for example, we have our A is equal to 20 and our B is equal to 3. If you are asked for the modulo, so if we say 20 mod B, commonly mod is expressed as this one, which B is 3. Sorry for this. So mod 3. So modulo 3. So we are actually asked what is the remainder when we divide 20 by 3. So using the long division method, no, to show the process. So what's 20 divided by 3? So this might be 6. Then 6 times 3 is 18. So 20 minus 18 is 2. So this is your remainder. So this will be the answer. No, 20 modulus 3. Our remainder is equal to 2. Okay, so this is Q is equal to A, which is A divided by 3. And Q will be equal to 6. And the remainder is 2. So this will be our result. Take note, 2 is greater than 0 and is less than B, which is 3. That's how we interpret this definition. Next is the GCD, or the greatest common divisor. Now, if you have two positive integers, we can find the common divisor among the two. Now, for all numbers, there's always a common divisor. It could be 2, 3, or even 1. Okay, if the common divisor is 1, so we have another term for that one, which will be discussed later on. Okay, another theorem, we have these theorems. No, uh, the positive integer d has a greatest common divisor. The positive integer d is the greatest common divisor of integers a and b, if and only if d divides a and d divides b. In short, d is a factor of both a and b. Whenever e divides a and e divides b, then e also divides d. So whenever there's a third or a fourth integer, no, which is a factor of d. So this theorem will be true. Then let a and b be positive integers. Okay, if you see a plus sign, that means this is positive integer. The letter Z represents the set of all integers. Okay, so this is positive integers. Okay, one. So this is the existential quantifier. There is a positive integer that is the greatest common divisor of A and B. Okay, there would exist D, or an integer. Okay, there exists an integer that is the greatest common divisor of A and B. So as I have told you earlier, for all the integers, there would always be a common divisor. It can be 1, 2, 3, or so on. Again, the theorem 2 states that let A and B be positive integers such that there exists a positive integer that is common, or that is the greatest common divisor. of A and B. And how do we get the greatest common divisor? But before that, there are other lemmas here. If e divides A, then negative E divides A. So that's what we have now in the example earlier. So that's 3 divides negative 9. We can also say negative 3 divides 9. So if A is not equal to 0, then the largest positive integer that can divide A is the absolute value of A. The greatest common divisor of two integers is equal to the greatest common divisor of the absolute values of the two integers A and B. The greatest common divisor of A and B is also equal to the greatest common divisor of B and A. So this is the commutative property. Then we have if A is not equal to 0 and B is not equal to 0, then the greatest common divisor of A and B exists and satisfies 0, which that is greater than the greatest common divisor of A and B, 0 which is less than rather the greatest common divisor of A and B and is less than or equal to the minimum value of A, absolute values of A and B. So this is now how we get the greatest common divisor. There are many ways, but we will use the Euclidean algorithm in solving the greatest common divisor of positive integers. Now, given A and B, so we can get the quotient and the remainders. Okay. Now we will not stop getting the quotient and the remainders until we get the last remainder, which is equal to 0. Okay. Until we will not get a remainder that is equal to 0, so this process will continue. Say, for example, if I have 20, if we go back to our example, 20 divided by 3, so this is our A, this is our B. So we have 20. So what's our quotient is 6 multiplied by 3, and that is plus 2. No? We have 6 times 3 is 18 plus 2, that is 20. Again, our first R sub 1 is 2, which is greater than 0, and is less than 3. So 0 is less than 2, 2 is less than 3. The next step would be copying, so this is 6, copying the B. No, kanin siya. And R, or moving them. So you have to remember, we will move R here, B rather, in the first line, and R sub 1 here. So what will happen? I'll get 3 is equal to 2. So 2 will be placed here. Then we'll get another Q and another remainder. So what will be our Q? So that's 1, then plus 1. So this is 1 times 2 is 2, plus 1 is 3. So we'll get a 3. Since we don't have a 0 remainder yet, so we will continue this process. We will move again this 1, no, R1, and also this 1. So we'll get 2 is equal to 1. So what do we multiply to 1 so that it will get equal to 2 or less than 2? So we multiply 2 and the remainder is 0. Since the remainder is 0, then we will stop. No? And we will get the last remainder that is equal to 0. And this is your last remainder. So we call it R sub K. The last remainder is actually your greatest common divisor. So the greatest, therefore, the greatest common divisor of 20 and 3 is equal to 1. This will be our answer. Next, determine the greatest common divisor of 372 and 132. So we'll follow the Euclidean algorithm. So that's A times Q, B plus R. So 372 will start here. So 372 is equal to AQ times 132 plus an R. So what do we multiply to 132 so that the result would be either equal to 372 or less than 372? No, the last value that is equal or less than to 372. So if we check, you have 132 times 1 is 132. 132 times 2 is 462. Let's try to have the other one. Add another 132. So this is 6, 9, and 3. Now this is greater than 372, so we will have this is 1, this is 3. So we will have a q that is equal to 2. So this is equal to 2. Then what is 372 minus 100, no, minus 264. So that's 8, 6, 0, we'll have 1. So this is 108. The remainder is not equal to 0, so we will continue the process. This is 132. Then move 108 here. So what do we multiply to 108 so that it will get a result less than 132 or equal to 132? Now 108 times 2 is 216, which is much greater than 132. So this is 1. So we'll just have to subtract 132 by 108. So that's 4. And this will become 2. So we'll have 24. Still not 0. So repeat process. So that's 108, which is equal to 24 plus a number. So we'll have here, so 24. We'll have to solve. So if you are going to program this, so you will use a loop, no, until it would be greater. When you stop when it's now greater than 108, then the last count subtracted by 1. So that would be your quotient. So since we don't have, you can use your calculator. Now to use your calculator, you can just, the easier way, instead of doing this manual counting, or this one man guessing, instead of guessing, so we can say 108 divided by 24. We can use that one. We can't use 5, I guess. Now since 5 times 4 is 20, and 5 times 2 is 10, and we have a carry which is 2, so not 5. How about 4? So I think we can use 4. So that's 16, 8, and 96. Yeah, we can use 4. And this is 2, this is 1. So the remainder is 12. The quotient is 4. Not 0 still. So this become 24. This is equal to 12 and a quotient and a remainder. So the quotient is 2. The remainder is 4. Therefore, the GCD, the greatest common divisor of 372 and 132 is equal to, what's the answer? 12. No? Take note that 12 is greater than or equal to 0, but is less than 132. We will not use this theorem here. Okay, I will just stick to this one. Okay, so this is our final answer. How about number 2? Okay. Number 2, the greatest common divisor for number 2 is equal to 986, 289. This is equal to 17. Check for yourself if that is really equal to 17. Okay, next, how about this one? 1692, 1692, and 1401. What is the greatest common divisor? The greatest common divisor of 1692 and 1401 is equal to 1. So I want you to show the solution in the engage section. So this will be your first engage problem. For number 2, okay, the solution is this one. Uh, I'll be just writing the solution. So that's 986 is equal to 289. The Q is the remainder 3. Kindly check if I have the correct answer. A solution of 119. You have 289 is equal to a quotient multiplied by 199. So that is 2 plus the remainder, which is 51. The next 119 is equal to a quotient multiplied by 51. So that's 2, I think. Yeah, 2 plus 17. Last, 51 times 17. So 34, so 3, and 3 times 7 is 21. So this is 0. Therefore, our GCD is 17. Okay, that's finding the greatest common divisor. Next, how do we know if a number is a prime or a composite number? So the first, we'll just use the theorem. No, just get the square root of that number. After, enumerate all the prime numbers less than that the square root of that number. Okay. Then, according to Euclid, there is an infinite number of prime numbers. Yeah, actually, there is still I think, an algorithm finding the largest prime number. Okay, I think that is the basis of cryptography. No, because in the concept of cryptography, the larger the prime number that you can generate, the more difficult it will be decrypted. No? Kung sa kwan pa, mas lisod siya i-hack if ko ang imuhang prime number. So there is still a computer solving for the largest number until now. Oh, okay. Let's go back with theorem 3. Now, P is a prime number and A and B are natural numbers. Natural numbers are numbers from 1 to infinity. Whole numbers from 1 to infinity. P is the natural number. Okay, let's determine if this is a prime or composite number. So again, the step is get the square root. Let's start with number 1, which is 31. We'll get the square root of 31. So the square root of 31 is if we count, we have 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, which means this should be less than 6. No, 6 squared is greater than 31. So what are the prime numbers less than 6? Of course, we will not include 1 since any number can be divided by 1. So we'll have 2, 3, and 5. So 4 is a composite number that is 2 times 2. Okay, let's check. Does 2 divide 31? No. Does 3 divided 31? No. Does 5 divides 31? No. Since 2, 3, and 5 does not divide 31, therefore 31 is a prime number. Okay, next, 57. So what's the square root of 57? 7 times 7 is 49. 8 times 8 is 64. So this is less than, no, 64, or the square root of 57 is less than 8. So what are the prime numbers less than 8? 2, 3, 5, 6 is not prime, so we'll go to 7, 7. So there are 4 prime numbers less than 8, 5 including 1, but we will not include 1 here. So we'll check. Does 2 divide 57? Of course not. 2 only divides even number. How about does 3 divides 57? So what's 57 divided by 3? 57, if you will check, this is 1, 3, 2, bring down 7, this is 9. Yeah, 9. This is 9. And no remainder, which means 3 divides 57. 5 does not divide 57. How about 7? I think not, because 7 times 8 is 56, which is 1, which means 7 does not divide 57. However, since there is one prime number that divides 57, therefore, how can I erase this? Okay, and just 3 triangular dots. Therefore, 57 is a composite number, or is not a prime number. How about number 47? Number 477 rather. Okay. The answer to this, no, you will be the one to solve, but I will give you the answer. The answer is composite number. So what are the numbers that divide 477? What are the prime numbers that divide 477? That's 3. Kindly check. No? Next, this will be part of your engage. This is now your engage 2. That's 907. So the answer is prime. So in the engage portion, show your solution or prove that 907 is a composite number. So that will be your second engage problem. And next, we have relatively prime numbers. So two integers, a and b, are relatively prime if and only if there exist integers x and y such that a times x plus b times 1 is equal to 1. For a, b, and c are positive integers. So if a divides b and c, or b times c, a and b is equal to 1, meaning the greatest common divisor of a and b is 1, then a divides c. So if a and b is equal to 1, okay, the divisor of a and b is 1, then we'll use this, and so on. In short, to get if numbers are relatively prime, we will still use the Euclidean algorithm, and if the greatest common divisor of the two is equal to 1, the GCD of A and B is equal to 1, then they are relatively prime numbers. When we say relatively prime numbers, though it can be that the number can be a composite number, no, one of which or two, one or two of them are composite numbers, both if both of them don't share the same factor except one, then they are relatively prime numbers. Again, if that among the factors of these two numbers, if they don't have common factors except one, then they are relatively prime numbers. For example, 2 and 20 and 9. So what are the factors of 20? So you have either 4 or 5, or you can have 2, 2, 5. So these are the prime numbers, prime factors of 20, 2, 2, and 5. 9 has 3 and 3. It can also be 9 and 1, and for 21 and itself. So again, we will not, of course, we'll have 1 here. No, that's automatically understood. There would always be a 1 factor. Okay, again, two numbers. So 20 and 9 are not prime numbers. They are composite numbers. But if you will check their factors, they don't have the same, or they don't share the same factor. No, 2, 2, 5. 9 has 3, 3, except 1. So if this is the case, then they are relatively prime numbers. And using Euclidean algorithm, so we will get their greatest common divisor. So we will start with 144. So here we have 144. This is equal to 43 times a number. Now, the quotient will be 3. The remainder will be 21. Kindly check. 15 rather. Oh, sorry. Okay. This is 15. Then next, we'll have 43, 15. So the quotient is 2. The remainder would be 13. Then we'll have 15. This is 13. And 1. This is 2. We'll have 13, 2, 6 plus 1. So we'll have 2, 1, 2, 0. So the last remainder is equal to 1. No? So which means the GCD of the two is 1, which means they are relatively prime numbers. Now, if in cases you won't see GCD here, okay, this is actually GCD. It was just not specified. But the GCD of, since the GCD of the two is 1, so they are relatively prime numbers. So that's how we solve, or we determine if two numbers are relatively prime numbers. Now, if you would compare it to program, these are the iterations. First iteration, second, third, fourth, and fifth. Now, the fifth iteration contains the last remainder, which is 1. For number 2, I'll just give you the answer. So you will have to solve, to show the solution or check. Now, number 4 will be your engage. So you have to show the solution. Number 2 and 3, just solve on your own. Okay, we'll check. No check. Okay. Uh, for number 3, they are not relatively prime. Okay, why? Because if we will show the solution, we have 8, 7, This is 1. The remainder will be 21. 8, 7, 21. Okay, this is 4 and 3. So you have 21. This is 3, 7, and the remainder is 0. So the greatest common divisor is 3, which is not 1. Therefore, they are not relatively prime numbers. Number 3, this is, yeah, the greatest common divisor is 1, so they are relatively prime number. Number 4 is you're engaged. Now you have to solve this, but the answer is not relatively prime number. So determine what's the greatest common divisor of number 4. So this is now your third problem in the engaged portion. Next, we have the least common multiple. Now, when we say least common multiple, the smallest multiple that is common to two or more numbers. So, for example, if I have 5 and 2, if we check, list down the multiples of 5, we have 5. 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15, 5 times 4 is 20. For number 2, you have 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10, then we'll have 12, 14, 16, 18, and 20. As you can see here, we have two common multiples for 5 and 2. We have 10 and 20 and so on. Now for the least, we have 10 and 20. Now, the smallest multiple, which is 10, will be called our LCM or least common multiple. Okay, the smallest multiple common to the numbers. It can be 2 numbers, 3 numbers, or so on. And how would we solve them? Okay, just like what I've done, we will be listing all the prime, no, the prime factors of the numbers. So let's start with number 1. 12 and 18. So what are the factors of 12? We can say that's 6 and 2, but we can get the prime factors of 6, and that is 3 times 2 multiplied by 2. So that's 3 times 2 times 2. Rearranging, so we'll have 2 squared times 3. So wala siya yung prime factors. How about for 18? 18 has 6 times 3. 6 times 3. 6 is 3 times 2 times 3. So that's 2 times 3 squared. Now to get the least common multiple, okay, let's change pen color. To get the least, okay, when you see expressions in this form, that means you're looking for LCM. But I will just put LCM para maklaro lang siya. So to get the least common multiple of 12 and 18, we will get the prime factors which has the highest order or highest exponent. Include also the prime factors that are not common to the two. Now, since here we have two common prime factors, 2 and 3, but we will get the prime factor which has the highest exponent. For this case, for 12 and 18, we have 2 squared and 2. Now, see, 2 squared has the highest exponent or order, so we'll have 2 squared. We also have 3 and 3 squared, so we will get 3 squared. So that's 4 squared is 2 squared is 4, 3 squared is 9. So therefore, the LCM of these two numbers is equal to 36. Now this is the least common multiple. And that's how we solve for the least common multiple. Next, let's try to solve number 2. That's 90 and 108. Okay, it's a factor of 90, so that's 9 times 10. You can do this way, or you can directly state the multiples, no, the prime multiples. You have 3 times 3, that's 9. 2 times 5 is 10. So rearranging, we'll have 2 times 3 squared times 5. Next, we have 108. That's 108 divided by 2 is 54. So if you don't have calculators, we'll have to manually calculate it. Factors of 54 is 9 times 6. So 9 times 6 is 9 is 3 times 3. So just rewrite it. 9 times 6 times 2. So that's 3 times 3. And 6 is 3 times 2. Then we'll have 2. So there are two 2's. So 2 squared. And there are 3 3's. So what will we do to get the least common multiple? Again, the least common multiple is equal to the prime. We'll get the prime multiples which has the largest exponent or order. So we have common 2, but 2 squared has the largest exponent or order, has the highest order. We have 3 cubed. Now 5 is not present in 108. So see here, which means this is equivalent to, we can also rewrite this as 5 to the 0, right? Now since 0 is just equal to, an inner number raised to power 0 has is equal to 1. So that's 5 to 0, 5 to the 1. But you don't need to write this for explanation purposes. That's why I'm showing this. Now, we will also include this one. Okay, that's 5. So that's 4 times 9 times 5. So what's the result? What is 4 times 9? That's 36. Sorry, this is 90. This is 108. Okay, you'll have 90 and 108. Okay, that's equal to, no, so 3, 3 cubed is not 9. 3 cubed is 27. So 4 times 27 times 5 is equal to 540. So this will be your final answer. So these are your final answers. Now how about for number 3? So the answer for number 3, so you have to do the same way for the 3 numbers, 2, 24, 26, and 108. So the result is the least common multiple is 2,808. Can you check? And number 5, let number 4 rather, the least common multiple is 280. Number 4 will be your engaged problem. So show the solution for the least common multiple of 5, 5, 56, and 70. No, sorry. The written is 20, 56, and 70. Okay. I think my solution is wrong. I've written 5, 20, and 56. So that's 20, 56, and 70. I will have to find the least common multiple of 20, 56, and 70. Okay, if the GCD is 1, the LCM is simply the product of the numbers. Meaning, if they are relatively prime numbers, then their greatest common multiple is just their product. For example, what's the LCM rather? The least common multiple is just the product of the two. In our example, we have 20 and 9. No, 20 don't share the same factors with 9. So therefore, their LCM is just 20 times 9, that's 180. To prove that's 20 has 2 squared times 5, that's 4 times 5. 9 has 3 squared or 9. Now, they don't share the same common factor, so that's 2 squared times 5 times 3 squared, or just 4 times 5 times 9, or 20 times 9, which is 180. That's how that's how we solve for the least common multiple. Lastly, for this session, we'll get the Euler-Stotian function. Now, the Stotian function just states that when you have a number, no, a number, we can get the number of prime, or the number of numbers. Okay, when you have a set of integer. Now, for example, if you have 20, if the number is 20, we can get uh, the number of integers relatively prime to 20. So that's Tothian function. Now, there are many formulas. Now, I have seen other formulas in getting the Tothian function of a number, but for this discussion, we will just use or follow these theorems. For example, if we want to get the number of prime numbers, the number of integers relatively prime to p, and p is a prime number, then the formula is just this one. The Tothian function of p, so this is phi of p. This is the lowercase, I think lowercase phi. The uppercase is this one. Okay, so this is read as phi. And that's equal to p minus 1. Say, for example, 7. Now, since 7 is a prime number, therefore, the numbers relatively prime to 7 is equal to 7 minus 1, which is 6. So what are the numbers less than 7? So you have 1, 2, 3, 4, 5, and 6. We will include 1. Thus, okay, in all the counts, 1 is included, no, as relatively prime to a number. So we have 2 does not divide 7, 3 does not divide 7, 4 does not divide 7, 5 does not divide 7, and 6 does not divide 7. So again, 1 is a special case. Next, if n is equal to pq, where p and q are distinct prime, for example, 10. Now 10 is equal to 5 times 2. So we can get the totient of 10, the phi function of 10, by getting its prime factors, and that's 5 minus 1 times 2 minus 2 minus 1. So that's equal to 4 times 1, or 4. Now, what are the numbers less than 10? 1, 2, 3, 4, 5, 6, 7, 8, and 9. So again, 1 is automatically included. 2 divides 10, right? And they share the same factor, which is 2. 3 does not divide 10, so that's 1. 4 and 10 has common factor, which is 2. 5 is a factor of 10. 6 has a common factor with 10. They are not relatively prime to 10 since it has a factor of 2. 7 don't share the same factor with 10. 8 does, 9 doesn't. So you have 9, 7, 3, and 1. So there are 4 numbers relatively prime to 10. Okay, that's theorem 2. If m and m are relatively prime numbers, okay, if m and n are relatively prime numbers, though they are composite number, then the phi function of m and m is just equal to the phi function of m and the phi function of n. Say, for example, 20 and 9. So that's 180, right? So 20 and 9. So we'll get the phi function of 20. The phi function of 20 and the phi function of 9. However, we have a special case here. If the number can be expressed into an exponential function, for a while. If the number can be expressed to an exponential function, then we will have to solve first. For example, this for this case, 9. Now, 9 can be expressed as 3 squared. So we can get the totient of 9 by 3 squared minus 1 and the phi of 3. So we'll have 3 squared is 3, 3 to the power of 2 minus 1 is 3. Then the phi function of 3 is 3 minus 1. Okay, that means 6. So there are 6 numbers relatively prime to 9. Yeah. Then for 20, note that 20 has factors 4 and 5. So that's 2 squared times 5. So using this special case, that would be uh, 2 to the 2 minus 1 times 2 minus 1. And since we still have 5, no, you have phi function of 2 squared times phi function of 5. Okay, that's what we'll be doing here. Then times the phi function of 5 is minus 1. So that's 2 to the 1 is 2 times 1 times 4. That's equal to 8. And phi function of 20 is 8. Phi function of 9 is 6. So we'll get 48. So the answer is 48. That's how we solve for. You can check your solution here at this website. No. So that's it. You have already solved 10. No, the phi function of 10 and 7. So that's phi function of 5 times 2, which is equal to the phi function of 5 equal to the phi function of the multiplied rather multiplied by the phi function of 2. So that's 5 minus 1, 2 minus 1. So that's 4 times 1 is 4. 7, since it's prime number, so that's just equal to 7 minus 1. So we have 6. 21 has factors 3 and 7. So we know that the totient of 3 is 2. That's 3 minus 1 and 7 minus 1. So that's 2 times 6 is equal to 12, and so on. Now, uh, what's the totient function of 17? So what's your answer? What is the totient function of 70? The answer is 24. Okay. Now for numbers 5 and 6, this will be your engage. So just choose one. This is your fifth item for the engage. Just choose one and answer. Submit your solution in the engage section of this um, module. So that will be all for today. We will discuss the number theory part 2 in the next session.